Hi, in this video I'm going to explain how to find distance between two loci, and here is a problem. A homozygous Grucho fly is crossed with homozygous Rab fly. The F1 females are test crossed with the following offspring produced, and here is a table with results, and the question is what is the linkage arrangements of this loci. And as usual, if you know how to solve this problem, I recommend you to stop video here, try to solve this problem on your own first, and when you would be ready, you can run video again and you can compare your answer with my answer and explanation. And first of all, I want to start with explain what is the test cross is. Test cross is when we use animal or fly in our example of the known genotype, usually it is homozygous recessive for both loci, to cross with unknown genotype, so later we can analyze the information that we got and we can tell what is the loci, if it is dominant or recessive, and so on. So also, if you take a close look at this table, you would see two distinct groups. This group happens in high frequency and this in low frequency. Why this happens? And here's explanation. So during meiosis 1, we may find such a picture like this. We may find two sister chromatids connected at the centromere, and one pair of such chromatids would be from the mother side and another would be from the father side, and we are diploid organism, so we have two sets of chromosomes. One would be from the mother side and another from the father side, and as you see, during meiosis each chromosome made a copy of itself. So here we would have a tetrachromosome when these two non-sister chromatids, so we call this chromatid, when these two chromatids are connected, and later when they get separated we call them chromosomes. So at the end of the meiosis we are going to get 4 chromosomes. But as you see, because we have one chromosome from the mother side, another one from the father side, these two chromosomes can be different in some certain places on the arms of the chromosomes, and we call the short arm P arm and long arm Q arm, and P stands for the petite or small arm. And imagine that we have different alleles. For example, here we may have alleles that is going to be capital A, and here we may have small a, and for example here we may have capital B, and here we may have small b. And during meiosis, two non-sister chromosomes or chromatids may line up and cross, make exchange of the arms. So crossing over might happen in many places, as you see, and the greater distance between two loci, the more chances that crossing over would happen here. And of course, because this is sister chromatids, here we also would have capital B and capital A, so these two sister chromatids would be absolutely identical as long as these two. But this chromatid and this one not necessarily should be identical, because one is from the mother side and another one from the father side. So as you see, we can have here recombinants. For example, one recombinant can be capital A and small b, and another type of recombinant can be small a and capital B. And here original is capital A and capital B and small a, small b. And of course here we also would have small a and small b. So this is going to be two recombinants, and as you already see, the greater the distance here, the more chances that we would have recombination. But imagine if we, for example, move this loci here in this new place, and this is going to be capital B here, and small b here. So this is going to be a new position, and as you see, the chance of recombination between these two loci would be much smaller. So the frequency would be much smaller. So if you take a look here, what we can tell that the frequency here is very low, and that means that the distance here also small. So now we can use the formula and find the distance in centimorgans, and here's the formula. So number of recombinants we have to divide by the number of total number of flies in our example, and multiply it by 100. And this is going to be our formula that we are going to use today in order to solve our problem. So number of recombinants here is 11. We have to divide by the total number, that is 1000. And what we are going to get here is 0.011. And if we multiply by 100, we are going to get 1.1 centimorgans. So this is going to be our answer. As you see, this is very easy. And also I want to add that centimorgans is not absolute number. And imagine, for example, that here in our example, this is chromosome number 1, and this is also chromosome number 1. They just came from the one from the mother side and another from the father side. But imagine, for example, that chromosome per 22 in humans would be much smaller than chromosome per number 1. And of course, 1 centimorgan of the chromosome 22 wouldn't equal to 1 centimorgan of the chromosome 1, because these two chromosomes size are very different. Another example would be, imagine that in your class you have people of the different height, and 1% of the tallness of the tall guy wouldn't equal to 1% of the tallness of the short guy. And this is all for today. Thank you for your attention. Please subscribe for my new videos that I post almost every day. Thumbs up if you like this video. Please write your comments, questions if you have any, and see you in the next video. Goodbye.